Today, we're going to talk about another way that we can find the equation for the least squares regression line. Remember, there are several ways. If we have the data, we can use the calculator or computer software to run linear regression. If we have the number summaries, we can use those formulas from your formula packet. And then finally, sometimes problems will just provide you with computer output. And the computer output has everything that you need to write your regression equation. And then we'll also talk about some things that you need to be cautious of when you're looking at regression models. So when we look at computer output has several important pieces of information, and there's a lot of stuff that's provided on the computer output because some of it we will use later this year when we look at inference for regression. But for right now, you need to be able to locate the slope, you need to be able to locate the y-intercept, and then computer output will also provide the value for r squared. Remember, that's the coefficient of determination, and s, which is the standard deviation of the residuals. So here's an example of Minitab output. And really, you're looking at, in this case, this is that non-exercise activity example where it was like fat gain and non-exercise activity. You have just labels over here on the left-hand side. So with Minitab, it tells you constant, and then it gives you your x variable. Y-intercept is always on top because it is your constant term in the equation. And then your slope is next to your x variable. So we can write our equation here. We can say that y hat is equal to 3.5051 minus 0.0034 x. Again, x being non-exercise activity change. So this first column here always gives you y-intercept and slope. Like I said, you can remember it as constant is written next to your constant term, and then your slope is written next to your x variable, and that's how it goes when you write your equation. Or you can remember that y-intercept is always on top and slope is on the bottom. The rest of this information in those top two rows is not important for us at this time. We will be looking at that later this year. The other numbers that you should be able to locate, you have S here, which is this 0.74 roughly, and then the R squared is 60.6. So that's the coefficient of determination. We will not be using this R squared adjusted value. Sometimes you will be asked to find R from computer output. So computer output does not provide you with the correlation, but what you can do is that you can find it from R squared. So if we needed R here, it would be the square root of 0.606. But we do want to be careful. R always matches the sign of the slope. So our slope here is negative. That means that when we take that square root, we have to remember to put that negative back in. So here, just keep in mind R sine equals the sine of the slope. Because if your slope is positive, you have a positive association, which means R is going to be positive, and then vice versa with the negative. Here's another set of computer output. It gives you the same thing. It's just oriented slightly differently. So you have R squared on top. Again, we don't use that R squared adjusted. S here is listed as root mean square error. So just a little bit different phrasing to identify. We don't need the rest of this information here. And then what you're seeing on top of the Minitab is just on the bottom of this set of output, but it does give you that same information. Again, we're just focusing on that first column for right now. It's in the same order of intercept on top and slope on the bottom. It's even a little bit clearer in this program. It tells you intercept is equal to 3.505. And then again, your slope is next to your x variable, which is how it appears in the equation. Again, we're not using any of this at this point in time. So in addition to being able to write your equation from computer output, today we need to talk about just some things to be cautious of when we're looking at regression. So when we look at the distinction between explanatory and response variables, it is important. You have two examples here where the x and y variables are changed. So here you have non-exercise activity predicting the fat gain. Here you're trying to predict non-exercise activity from fat gain. This is really what we should be looking at. It makes sense to predict fat gain from non-exercise activity, not the other way around. But what you do want to look at is how drastically some of these calculations change if you mistakenly flip the explanatory and response variable. Your equation is very different. So if we look here between the two equations, your y-intercept of 3.505 is very different from your y-intercept of 745. Same thing with slopes, very different slopes between the two. Your values for S also differ. However, your values for R and R squared do not change. So say R and R squared remain the same. Your A, your B, and your S for standard deviation of the residuals are different. You should only use correlation and regression to describe linear relationships. So if something is curved, then you should not be using the lin-reg function on your calculator. We will start to look at some curved relationships later this school year, but for right now, we're just going to focus on straight line relationships. And then we talked about the fact that outliers can impact your regression equation. And so here is an example where you have some outlying points. You have child 19 here, who's an outlier in the vertical direction, and you have child 18 here, who's an outlier in the horizontal direction. If we were to look at our residual plot, you would see that outliers in the vertical direction, like child 19, often have large residuals. Because it's vertically very far from that line. However, outliers in the horizontal direction they often pull the least squares regression line towards them. So over here on the left, you can see that this is really influencing the least squares regression line to have a steeper negative slope here to pull it towards child 18. So outliers in the horizontal direction often have small residuals because the line is pulled towards them. So here's just an example of the equation, and I can get rid of what I've written on top of here so we can see it a little bit more clearly. But we've got calculations here with all of the children and then removing those outliers. So you can see the lines on the graph. And so if you were to remove child 19, who is the outlier in the vertical direction, you can see that things don't change a whole lot in terms of your equation. It's still pretty similar. Your correlation does go up slightly. If we take out child 18, the outlier that's in the horizontal direction, we see that it does influence that equation quite a bit more, and it also influences that correlation. The correlation is also actually strengthened with child 18 because it's pulling that data towards that straight line, whereas if we got rid of it, there's a little bit more of a random scatter going on in this group. And so that gets at what we call outliers and influential observations. So here we call something an outlier if it just lies outside of the overall pattern. And so the outliers in this case would be both of those children. We consider something an influential observation if it's going to drastically influence the calculations of the least squares regression line. So points that are outliers in the X direction are often influential points. Many times influential observations are also considered high leverage. So high leverage basically have much larger or much smaller X values than the other points in the data set. And think of it like this. They're outside of that range of X values, but they pull or kind of leverage the line towards those points. So we'll say here, points can be influential and high leverage at the same time. So in this particular example, I would say child 18 is both influential and high leverage. It's an outlier in the X direction, so that makes it high leverage. It's leveraging or pulling that line towards it. And then it's also influential. The calculations here are fairly different, I should say from the original to this one when we remove that child. Child 19, while it's an outlier, it's not really impacting the calculations all that much. They're slightly different, but not drastically so. And it's not an outlier in the horizontal direction. So child 19, we would say this child's an outlier, but it's not high leverage and it's not influential. Just because you see an association between two values or two variables does not mean that one causes the other. So we do want to be really careful about trying to say something causes something else. When we get into chapter 4, we will talk more about some things that need to happen with experimental design in order for us to try and imply causation. So here's an example that kind of makes it clear as to how we can have this strong association, but not necessarily one thing causing another. So here they're showing in this study, people with 2 cars live longer than people with 1 car. 3 cars live even longer. So they're saying that there's a very high correlation between the number of cars and life expectancy. But it would be silly for us to think that if we want to live longer, we should just go out and buy more vehicles. There are other variables at play there. So those individuals that have the income to purchase more cars probably also have better access to healthcare and other things that are helping them live longer. So we did learn a lot in section 3.2. We want to make sure that we know that the regression line, linear regression, and least squares regression line are all interchangeable terms for us at this point. We want to come up with an equation that will allow us to predict a y value from a certain value of x. So we're going to be able to find our slope and our intercept in several different ways. We should be able to find them using technology if we have the original data set. We should be able to find them using the formulas if we have the numerical summaries. And then we should also be able to find them from computer output. In addition to calculating the slope and the intercept, we also should be able to interpret them. So your slope is what you're predicting to happen with y as x increases by 1 unit. And when you talk about your slope in context, that word prediction is very important. Same thing with your y-intercept. It's what you predict to be the start value of, or what's predicted to happen when x equals 0. We do want to make sure that we're avoiding extrapolation, which sometimes gets tied back to making a prediction with that y-intercept. If your x variables are very far from what you're trying to make predictions for, so your data set is very far away from your predicted values, then that means that your predictions might not be accurate. So try not to go too far outside of the domain of your original data set. Again, our least squares regression line, or LSRL, is called that because it is minimizing the sum of the squares of those vertical distances between y and y hat. And those vertical distances are our residuals. We can also make a residual plot. So when you're looking at a residual plot, remember that you're looking for just a random scatter. If you have a random scatter in your residual plot, and we'll also say with small residuals, that means a linear model is a good fit for the data. If you do have a random scatter and those residuals are large, it doesn't necessarily mean that another model would fit better. It just means that the linear model might not be all that accurate because your points are far from the line. You should be able to find S from computer output and know that S looks at the average or typical variability between y and y hat. So the smaller the S value is, the better, because we're saying that those points are very close to the line. You should know that R squared is the coefficient of determination. You should recognize that as the fraction of variation or percent of variation or proportion of variation. Anytime you see that, that should be a red flag that you're looking for R squared. So you should be able to find R squared from computer output, from your calculator. You should also be able to find R squared if R is provided just by squaring the value of R. And then just when we look at our scatter plots, we do want to make sure we're looking for outliers, influential points, and those high leverage points. As far as the outliers go, there is not a check for outliers in chapter 3 when we're looking at 2 quantitative variables. So it's just something that doesn't fit the general trend. And again, like the last example, we don't want to necessarily say that one thing causes another at this point. We need to talk about study design before we can even venture towards cause and effect. So here's your homework assignment for tonight.